Every year, India is torn apart by two extreme opposing forces. The north and east face torrential downpours that wash away entire villages, while the west and south suffer through months of bone-dry soil. For millions living in the flood zones, the annual deluge means abandoning homes and leading livestock through shoulder-deep, murky water just to survive. Meanwhile, farmers in the drought-stricken regions watch helplessly as their crops wither in deeply cracked earth, pushing rural families into severe economic distress. Looking at these two extremes, you might assume the country simply doesn't have enough water, but that is not the case. The crisis is a massive geographic and temporal imbalance. India receives roughly 4,000 billion cubic meters of precipitation every year, more than enough to sustain the entire population. The problem is the timeline. 80% of that massive volume falls in a concentrated 4-month window between June and September. And it does not fall evenly. The vast majority of this rain is dumped on the Himalayan catchments and the northeast, the areas glowing on the map, while the peninsular and western regions are left completely dark. To survive the dry months in those dark zones, millions of people have to pump water from underground aquifers. Because of this constant demand, that groundwater is depleting rapidly. The engineering challenge is clear. To fix the imbalance, you have to capture the massive surplus of the summer monsoons, store it, and physically transport it thousands of miles to a starved continent. For decades, the standard approach was to build localized dams in individual river basins, but that barely captures enough surface runoff to keep pace with demand. Solving a continental problem required a continental grid. In 1978, Captain D.J. Dastur proposed a massive master plan designed to permanently end the cycle of floods and droughts. He called it the Garland Canal Project. The first half of the blueprint focuses on the north. A 2,600-mile canal sweeps across the map, tracing the periphery of the Himalayas. It sits exactly at a 1,200-foot elevation to intercept the flow of glacial streams and eastern rivers before they flood the plains below. Then, a second line draws around the central and southern plateaus. This 5,800-mile network is locked in at a 1,000-foot elevation, positioned to capture the monsoon-fed rivers of the south. Pipes then bridge the gap between the two systems. By locking the northern canal at an elevation 200 feet higher than the southern network, the entire grid functions as a unified, gravity-fed loop. This incredibly clever configuration allows millions of acre-feet to move across the subcontinent without requiring any external pumping energy. This diagram shows how the water reaches the fields. The main canal branches out into a herringbone pattern of smaller, subsidiary canals. If an area is dry, water flows outward to hydrate the soil. If a basin is heavily flooded, the canals drain the excess inward, controlling the exact depth of the water table. By doing this on a continental scale, the project aimed to expand the nation's irrigated land footprint to 540 million acres. That volume of reliably watered soil would ensure absolute food security for a growing population. Beyond agriculture, this interconnected grid would generate massive amounts of hydroelectric power at its drops, while creating a vast, zero-carbon inland shipping network to transport food and raw materials. On a purely mathematical and engineering level, the Garland Canal transforms a geographic liability into an engine of national prosperity. It applies precise engineering to completely rewrite the environment. India's National Water Development Agency has studied dozens of localized interlinking projects based on these same ideas, and they all face immediate hurdles. The financial cost of building these colossal reservoirs, tunnels, and canals stretches into the billions of dollars. The larger danger is blocking a river's natural path. This cross-section shows a dam trapping nutrient-rich silt, leaving downstream soils barren over time. Without fresh water pushing to the sea, ocean salt backs up into the delta. Downstream basins become saline, destroying their agricultural productivity entirely. Those floodwaters that rush out to the ocean are often viewed as wasted. In reality, they perform vital ecological maintenance, flushing out salt and delivering nutrients. A rigid canal system actively breaks that cycle. Creating the reservoirs to feed these canals means flooding thousands of acres of inhabited land. Whole communities find their homes and farms submerged, displacing rural citizens and severely disrupting local fisheries. there are also international consequences. Altering the flow of shared rivers, like the Ganges and the Brahmaputra, directly impacts the water supply of downstream sovereign nations, like Bangladesh, leading to intense geopolitical friction. When you zoom out and look at the map as it glows with these artificial arteries, you see the sheer scale of the ambition. It is an attempt to manually tune the hydrology of an entire subcontinent. The math tells us we can move the water. The engineering tells us how to do it. But the unresolved question remains: is the promise of ending droughts and floods worth the permanent, unpredictable disruption of the natural order?